This lesson is about the partial autocorrelation function. We are going to introduce the sample partial autocorrelation function, which is an aid that complements the sample ACF when we have to identify a stationary model for the random term that we get after pre-transforming to make the variance approximate constant and after differencing. Pre-transforming and differencing is something that we did in the previous lesson to obtain a random term that is stationary mean and stationary in the variance. At that point, the ACF helps us determine whether the random term is really stationary, and the ACF and the PACF help us identify a model. So the PACF is particularly useful to identify a model when the random term, after we have difference and so on, has the sample ACF of an AR process with large coefficients. That means an AR process that is almost non-stationary, close to stationary. Why is that? Well, AR processes like that tend to have similar shape and shapes very similar to the ACF of a non-stationary process. So it's very hard to determine what is the order of the model that we need to take into account in modeling. So their ACF is not much help. It is for these kind of processes that the sample PACF is very important. Not so much when the ACF is the ACF of a moving average model. So why is it important to know this? Well, it's important to have as many tools as possible that help us choose models that are not very big. Models that are not very big, we call parsimonious models. Models that do not have a large number of coefficients. We like usually modeling to follow the KISS principle, keep it sophisticatedly simple. The sample PACF helps us avoid fitting noise, which is what you get when you fit large models. So the sample PACF help us follow the KISS principle when we are identifying a model. And practitioners need to know about the sample PACF as one of the tools in their practice that helps them select these parsimonious models when used in conjunction, when the PACF is used in conjunction with the ACF. So in the fourth step in ARIMA modeling of the Johnson-Johnson in a previous lesson, we saw this sample ACF and sample PACF after we logged the series to stabilize the variance, took first order difference to get a stationary mean time series to remove the trend, in other words, and seasonal differencing to account for the seasonality of this quarterly time series. Okay, so these are the ACF of that very transformed time series and the PACF. And we said there that we will tentatively identify an ARIMA 011, 010 model to the logged earnings. That's one way of expressing an ARIMA model for a time series that has been differenced, regular and seasonality. And it doesn't reflect this notation that we took the log. So that's something that we keep in our record keeping as we do the preliminary steps of ARIMA modeling. So more on these models is coming in a later lecture after we study stationary stochastic processes in theory. In this example, the ACF tells us that we do not need the sample PACF much. It's not telling us in words, but we are interpreting it that way. The ACF, and again, you don't need to know that right now, I'm just telling you, is the ACF of an MA moving average process of order 1. We could be wrong though, so maybe we have an ARMA 11, but again, talking about one model, these two functions are helping us identify is kind of not necessary right now. It will be clear after we study stochastic process models. But by looking at the ACF, I can tell that it's the ACF of a stationary process, not the typical ACF of a time series that has a trend. So contrast the previous picture with the one that we have here. This is the US population, decennial US population that comes with base R, is one of the time series there. So notice the smoothness of this sample autocorrelation function. For these kinds of time series that have this autocorrelation function in which we have R1 significant, R2 significant, R3 significant, or worse ones in which we have a lot of, quite a few of the first lags having R sub k's that are statistically significant. For these kinds of time series, the sample partial autocorrelation function is very useful. Look at the simplicity of the sample partial autocorrelation function. It's just giving us that the partial autocorrelation is 0.8 and nothing else. The rest are not statistically significant and very clearly. So in this case, we will say that this US population follows an AR process of order 1. And we didn't transform or anything like that. So the pattern in the ACF, as I say, is typical of some AR processes. But again, in this case, you will say, oh, we could choose order 3, but order 3 is kind of long already. So if you choose just order 1 based on what you see in the PACF, then you'll do better. So that's what the PACF is for, to help us make our models smaller, particularly when the ACF is that of a AR process. Again, do not worry too much about what all this means. Just try to get in your mind that when we get to the point of having to identify a model, the PACF is needed. So what is the sample partial autocorrelation? Sample partial autocorrelation coefficient at log K, and we denote it as R sub kk to distinguish it from the R sub k, which is the label for the autocorrelation, is defined as follows. The R sub kk will be R1. So in other words, R sub 1,1 is just the first R1. And the other lags, for lags k equal to 3, R sub 2 will be R sub 2 minus the sum from j equal 1 to k minus 1, right? In this case, we are doing 2, so that will be 2 R1, right? Minus, you have to do several iterations, right? For j equal 1 to 1 in this case. So R sub 2 minus R sub 1 divided by 1 minus this operation. So it's kind of tedious to calculate. And the other R sub kj's, that the ones that are also going to be partial autocorrelations, are calculated using this iterative kind of algorithm. So the standard error of these summary statistics, this is a summary statistic, so it's a sample statistic. So it's an estimate of something. So it's a random variable and therefore has a standard error. And therefore you calculate the t statistic by dividing your R by the standard error. And you implicitly, by doing that, are doing a test of hypothesis of the following parameters, right? So this will be the population sample partial, that will be the population partial autocorrelation coefficient, and you are testing when you are looking at your partial autocorrelation whether the partial autocorrelation in the ensemble population is 0 and the partial autocorrelation is not 0 as the alternative. So if the t statistic is larger than 2 or smaller than -2, we are going to reject the null hypothesis. That means that the partial autocorrelation is statistically significant. So that's what the vertical bars outside the blue horizontal lines mean. When they are outside the horizontal bars, let's go back to the picture here. Notice how 0.8 is outside. the two standard errors bar means that autocorrelation at the first lag is 0.8 and it's statistically significant, right? So we reject the null hypothesis that the partial autocorrelation lag 1 is 1, right? Is 0. That's what is being done when we do a plot of a partial autocorrelation. So what is the interpretation of all that? Well, you know, the interpretation is not straightforward. You just have to imagine that the autocorrelations, which are the coefficients rho that we introduced in earlier lectures, are a function of past autocorrelations. So if you start writing these kind of regression models of autocorrelation at lag k as a function of autocorrelation at lag k minus 1, and you write a model of autocorrelation lag k with autocorrelation lag k minus 1 and k minus 2, the coefficients that go with the last term in these regressions are the partial autocorrelation coefficients. Therefore, you can interpret them as you interpret regression coefficients. The regression coefficients in a multiple regression model, it just tells you the effect of that variable in which the coefficient appears on the dependent variable, in this case, the rho sub k, controlling for the effect of the other variables. That means remaining the effect of the other constants. So that is the interpretation of the partial autocorrelation. If we denote our time series by yt, then these parameters are telling us the autocorrelations of yt with yt minus k after you remove the effect of the other autocorrelations at the smaller lags, right? And that's why that's important in an AR process. AR processes have a lot of inertia, right? And they are the trendy kind of time series, but not trendy so much that they are non-stationary, but they have these kind of long waves or kind of long periods with small trends and so on. And therefore, there is high correlation, but because of the inertia, one year is affected by the other year and so on, you don't see, you cannot see much. And so this is like in the example that we were seeing here, right? There's this kind of inertia, this kind of a smoothness in the autocorrelations. And in order to see really what is the process going on, we need the partial autocorrelation. Partial autocorrelation is clean, very clean. It's telling us the autocorrelation of yt with yt minus 1 is significant, but not the other ones, right? So the autocorrelation of yt with yt minus 2, although in the ACF appears as significant, it's not significant really when you take into account the previous autocorrelation. So when you take into account the intermediate autocorrelations, there is not, which are affecting the next one, the pure effect of that lag 2 or lag 3 or lag 4 is not going to be there, okay? So that's the pure, so it has in some ways some purity interpretation. It helps us see what the AR, the sample autocorrelation of an AR process doesn't let us see because of the inertia, okay? So that's the important thing to keep in mind. And again, notice one more thing, that the sample partial autocorrelation does not have always autocorrelation at lag 0 equal to 1. In the sample partial autocorrelation, you can start immediately interpreting the first lag. Okay, so remember that in the ACF, we did not interpret lag 0 at all because it's always 1. Autocorrelation of a variable with itself is always 1. And that's not the case with a sample partial autocorrelation. So here's a question for you that we can answer elsewhere. Why are the lags depicted as they are in the horizontal axis? 20, 40, that looks like a lot of lags here. what is peculiar about this time series for R to have the lags in the horizontal axis this way? So let's see what we learned in this lesson. In practice, each time series has its own combination of ACF and PACF that helps us identify a Riemann model, and we'll see many more when we see stochastic processes. And we define the sample partial autocorrelation and explained test of hypotheses that we are implicitly doing to understand which partial autocorrelation is statistically significant. And we also interpreted the partial autocorrelation coefficients as regression coefficients. And notice that the partial ACF does not have lag 0. Therefore, doesn't have a partial autocorrelation equal to 1 in all the PACF. I hope you enjoyed this lesson, and we will be applying this sample partial autocorrelation function as much as the ACF when we start the modeling, and also in the theory of stationary stochastic processes, which will come in a future lesson.